Complete each table. Use your results to describe in words what the end behavior of the outputs and the inputs move further away from zero. Sketch the end behavior. The first function of the rational is a parent function. Okay. So if I have 1 over x, okay, 1 over x, and I'm going to have, if I plug in 10, actually, you know what, let's make a little table here. So if I plug in 1 over x, 1, so here's x, here's my function, and so if x is equal to 10 or 10 to the third power equals 10 to the third power, which is also known as 1,000, or 10 to the 6th power, or 10 to the 9th power. Okay, then here, what will pop out of my function? Well, this is equal to 1 divided by whatever this number is. So it's 0.1, as you can see here, 0.1. And then let's go over here. And you can see that it gets really, really small. By the way, 1e to the negative 9 basically means 1 times 10 to the negative 9, which is actually 0.000000001, which is a really small number. It's effectively close to 0. All right, what happens if we make these negatives? Well, it just makes this thing negative here, and this thing negative, this thing negative, so on and so forth. All it does is it changes these numbers to negative numbers. Huh, I wonder why this thing doesn't equals negative 1 million. There we go. Ah, whatever. All right. So all it does is it actually kind of still tapers off to 0. It just tapers off on the negative side. So the end behavior would look like this, because as it goes further and further out, you get closer and closer to 0, and as it goes further and further out, it's negative, but it goes closer and closer to 0. Now, let's try the let's see. What about the end behavior of h of x? And let's say h of x is similar to f of x, but we plug in x minus 100. So we add the difference between this one's just 1 over x, and this one's going to be 1 equals 1 divided by this minus 100. Okay, so this is function 2. So let's copy down this thing right here. And here's my point, okay? This number right here, when I have it at x equals 1,000, is 0.001, but over here it's 0.0009, which if I round that off, that could round up to 0.001. This number right here, it's saying it's exactly the same. It is not actually exactly the same. It's just the difference is so small that it's not that the computer can't tell the difference, it's that the difference is insignificant. So even though I added this minus 100, and you would assume that 100 is a pretty big number to deal with, the properties have the same properties as 1 over x. Like the properties of this function right here have the same properties as 1 over x when you're talking about the end behavior. So if this is the end behavior of 1 over x, then I would say that the end behavior of 1 over x minus 100 is going to be the exact same thing. So if I'm asking, why do I think the end behavior of 1 over x minus 100 is the same for f of x equals 1 over x? Well, my answer is because when you're talking about positive infinity, where you're letting x go to really, really large numbers or really, really small numbers like negative infinity, the minus 100 basically can be disregarded. And so basically you have h of x is approximately equal to 1 over x, and f of x is equal to 1 over x. So they're the same function when we're talking about x being really, really small extreme numbers.